Okay, so in this video we're going to be looking at linear regression, and so this is the most basic problem in machine learning. And for this I'm going to show you an example using the classic example that everyone uses, that is predict the price of a home based on a set of features. Okay, in this case we're going to be using only one feature, which is the number of rooms of the house, and based on that we're going to predict how much a house costs. Okay, so if it has one room, it costs $1,000. If it has two, $2,000, three, $3,000, and four, $4,000. Okay, so this is just an example. Okay, it's not real. So with these data points that we have found, or we have researched in some way, we can make a straight line. Of course, more strict than this, of course, and you may call this, of course, this is pretty simple, with y that is equal to a times x plus b, where this is the BS term, this is the slope, this is the independent variable and the dependent variable. Okay, but in this case we're going to explain this in a more vectorized way, for which theta is the parameter which is going to enclose this term and this other term, and x is the input data that we have. Okay, so we're going to define now these features x and these parameters. So x belongs to a vectorial space of m times n, where m is the number of samples or observations that we get from our problem, and n is the number of features. So this n can be can have many dimensions. There are problems in which they use even 1,000 features in order to predict something. Okay, and the parameters which is going to be denoted by theta, belong to a vectorial space of one row times n plus one column. Okay, so where n is the number of features, as we have seen before, and this plus one is used for the BS term. Okay, so you have to think of this as theta sub 0 times x of 0 plus theta sub 1 x of 1 in the case of this problem, where x sub 0 is always going to be equal to 1. So this is going to be theta sub 0 plus theta sub 1 times x of 1. Okay, this is the BS term, this is the parameter for the slope of our function, and this is the input. Okay, so of course you may have some background in machine learning so far, and you know that the input, the features that you have a number of samples and a number of features, and based on that you're going to create these plots. Okay, so now we're going to be talking a little bit about the type of data that this problem works for, and it is that the features have to be continuous. It can, of course, we're using integers in this case, but they can be continuous. You can use double precision or single precision variables, and that the outcomes have to be continuous as well. The outcomes refers to the predictions, okay, to the outputs. So it is required for this problem that both are continuous in order to, so that it can work well. Okay, otherwise you're going to have kind of a little bit of problem. So now we're going to move, in order to make this not so complicated, we're going to be hey, what the hell happened? Okay, so now we're going to be looking at the components of this problem of linear regression, and these three components, I like to address them in all the machine learning problems, because they're the basic stuff that you can work with, and you can program this very easily. Okay, so we're going to start with the hypothesis. The hypothesis is the function that you're going to create in order to imitate the features and the parameters that you already have from your observations, and this hypothesis has x as the input, and theta, which is, as we have seen, the bias and the slope, okay, of our problem. But we're going to create a new theta, we're going to tune a new theta that is going to predict for new outcomes. So this means that this value theta, which we call the parameter, is the one that is going to learn from our function. Okay, and so we're going to tune this variable theta, as you will see with the next steps, that are the cost function and the learning function. Okay, so we're going to start with the cost function. I haven't written anything here because it's preferable to explain you this. And so we define the cost function as being g of theta, which is equal to 1 over 2 times m, where m is the number of samples of our input variable x, times the summation of I, that is equal to 1 until the number of samples of our hypothesis, h of theta sub xi for each of the samples, minus y sub I. Now, this y sub I is the predicted values from our observations. Okay, so for this we're going to define three vectors: x, which is, as we have seen, a vectorial space that belongs to m times n, right, being the samples and the features. We have theta that belongs to the vectorial space of 1 times n plus 1. We have said that this plus 1 is for the bias term, and there is another one, which is y, that belongs to a vectorial space of m times 1. Now this y is the label data, is the data that we already have that comes with the observations, because we're working with a supervised problem, with a supervised learning problem. So what we do right here is that we take the hypothesis using theta transpose times x, and we subtract that from our level data, of course. So if this is going to give us 1 and the output is 1, this is going to become 0. If this is 2 and this is 1, then this is going to become 1. And so we square this, and with this we can obtain the root mean squared error. Now with this root mean squared error, we can quantify how much our theta variables are differ from the actual x and y. Okay, and so with this we're going to take advantage of this in order to make our algorithm learn. Okay, so from there we just need to add the regularization term, which is plus lambda over 2 times m times the summation from j that equals 1 until n of theta sub j squared. Now remember that this is the parameters that we use for function to learn, and this from right over here, which is called the regularization term, is a term that allows us to avoid overfitting in our function. Now I'm going to explain overfitting in another video, but the only thing that you need to know is that this term right over here is very useful whenever we want to train our theta values. Okay, so we're going to leave this right over here. We're just going to explain this lambda term that is used to penalize our theta. So if we increase lambda too much, this means that we're going to have high penalization in our theta parameter. Okay, but if we have a very low lambda, then this means that there is going to be low penalization. If we have high penalization, then we are going to prevent overfitting. But if we have low penalization, then we're going to probably get we're going to get a lot of overfitting, because there is not going to be penalization. Now we have to be careful with this, because if lambda is very high, then we may get bias. So we need to tune this variable by making plots, as you will see later in the code. Okay. Okay, so passing from this and having talked about this, we can now move to the learning function. This is the central part, because it's where the code, basically how we make the code. And for this we're going to be using the batch gradient descent. This algorithm is used to find the local minimum of a function. Okay, so we use repeat, and this repeat behaves as this: theta sub j is equal to theta sub j minus alpha divided by 2m times, we're going to vectorize this, h of theta sub x minus y multiplied by x sub j minus lambda over m times theta sub j. Okay, now there is something, we're going to close this, and we're going to define this from right over here. If you can know this, if we apply the derivative of the cost function with respect to some value of with respect to some parameter, we're going to obtain right over here, this thing from right over here, because we use 2 over 2 times m, so these two go, times the summation from I that is equal to 1 until m of h of theta sub x minus y sub I and plus lambda over 2 times n times 2 theta sub j, and of course the summation for each of those. So we kill this, and we're going to multiply this by this, and so this is equal. Okay, this is equal. Yeah, I forgot. From right over here, we need to multiply this because it's chain rule, right? First, we just drop the coefficient from the exponential coefficient, and then we derivate what is inside. Inside, we know that our hypothesis is theta transpose times x, in this case theta sub 0 plus theta sub 1 times x sub 1. So if we derive with respect to theta sub 0, this is going to become 0 and this is going to become 1. But if we derive with respect to j that is equal to the feature 1, then we're going to have that theta sub 0 is 0 plus x1, because this is going to become 1. Okay, and so that's why we multiply times the feature that gets derived thanks to this theta. Okay, so this is basically the batch gradient descent, and there is only one term that I am not mentioning yet. This alpha from right over here is the learning rate. This tells you how fast your algorithm will learn. If this is very high, you may get into some problems of overfitting that are going to be explained in another video, because this is going to become very long. But if this is very slow, your algorithm will take a lot of time to compile and will take a lot of time to learn, but you are going to still okay, I'm going to give you values so that you can work with this. So the values that you can use for this are minus 0.5 to 0.5. Okay, but just as a quick thing, the only thing that you need to know is this from right over here, that you're going to tune these theta values using this batch gradient descent. Now there's only one more thing that I'm going to explain you in the code, but theta sub j, this thing from right over here, means the parameters, right? And we have n plus 1 parameters. You apply this regularization term for all the theta except for j that is equal to 0 for the bias term. So whenever you're working with your vector, you have to avoid making a penalization of the bias term. Okay, and so that is what we're going to check in the code. So I will also like to show you some contour plots and some 3D plots about how this works, but the video may get too extensive, so we're just going to go straight to the code. Okay, so we're starting importing all the libraries that we will need. If we will need time, matplotlib, we're going to use ggplot to make some nice plots. Easy to understand. We'll import pandas, numpy, and sklearn just to split our dataset. Okay, now we're going to create a main method. From our main method, the first thing that we will do is to define our constants, such as alpha and lambda, which refers to lambda. And the next thing is that we're going to load the dataset of diabetes from the sklearn module. Okay, so that is a little bit tricky. We need to set as an array for the level data, and next that's going to be just the data. Okay, then we're going to apply some normalization to our data set. For that, we're going to implement that function that you can see from right over there. It's very easy. It's just the matrix minus the maximum, minus the minimum over the maximum minus the minimum. Then we're going to use the sklearn method to split our data set into a training set and into a test set. We're not going to be using cross-validation test set. Next thing, we're going to be adding our bias column of features that we have talked about, the x sub 0, and we have to do the same for the train and for the test dataset. Okay, so the next thing is to create the theta variable, which is going to give us our parameters. Remember that it has to be n plus 1 features, and then we're going to define our cost function. In our cost function, we're going to compute the cost of our function with respect to the theta, and for that we're going to create a new theta that is going to contain all except for the first bias term that, remember, doesn't have to be regularized. So we're just going to use numpy functions in order to make our our cost, and as you can see, theta is being used in the second term of the regularization term, avoiding the BS term. Okay, then we're going to return our cost, and we're going to add the correct parameters to our function in order to append our values. We're going to append to our values to show that our function is learning and that the parameters learn over time. Okay, the next thing is that we have to create the gradients. The gradients are the derivatives of our cost function with respect to each of the parameters. For remember that we have to separate theta sub 0 and theta sub j, and for this we're going to create theta sub 0, which is kind of similar to the previous function. Just remember that we have to multiply our derived feature, and remember that for theta sub 0 there is no derived feature, it's just one, but for the second one it really is. Please take a look at a little bit about the code. There are some matrices that need to be transposed as in the theta sub j, and basically it's the same for the rest of the gradients, right? It's just the derivative of the cost function. So so far we have the gradients, we have the cost function, and we have to return in the gradients function the theta sub 0 and the theta sub j. So now we're going to update the values of our theta values, and for that we're just going to be using the alpha learning coefficient that we have seen before, and we're going to append the result in order to check that our model is learning over time. Now we're going to be using the sklearn model in order to make our function learn from the data using the sklearn model, and we're going to compare the results to see how well our algorithm is doing with compared to an algorithm that is with a library that is very popular on the internet. Okay, you will see that we are going to have we're going to have very similar results, and it's better because we have more parameters to tune than the sklearn function. So for that we're just going to append the necessary values, and we're going to plot our function. Okay, so now we will go straight to the code, and the code there are some things that you have to do before the start. Okay, and the first problem that we had is that there is no need for normalization in the diabetes database, because the database is already normalized. So if you normalize again, you're going to have a very high cost in your cost function, and your parameters will never learn. Okay, so in order to show you that, we're going to actually compile using the normalization, and you're going to see how the parameters don't get to the correct value. Okay, we have to wait a little bit as I'm recording the screen, and this is going to take a lot of time, and oh my god, we're just waiting a few seconds. We just kill the process, and we wait a little bit more. Okay, we have, there you go. That is the exponential function that you see, and now we're going to check. We're going to take a look of the function that doesn't fit at by any means anything. Okay, so now we're going to comment the part of the normalization. However, this is going to still going to work for you because other data sets are not going to be normalized. Okay, as you have seen, we have the normalization, and the predict function is very equal to our own function that we have done with our own prediction. Actually, I think that our error is a little bit better than the one given from the sklearn model, and it is because we're able to modify our lambda and our learning rate constants. Okay, so if you increase the value of the lambda, we're going to increase the error because we're going to start entering into a bias zone in which our model is not going to fit pretty well. Okay, and if you start seeing our model start becoming a little bit kind of different, having a lot of error, that's something that we don't want. So this lambda term, you can tune it by yourself, but there are also some automatic methods in which you can use another set of data named the cross validation, and you take that from your training from the training set. But the problem is that you're going to lose a lot of data just to tune some of the variables, so it's not worth it. And in my opinion, I think it's better to tune this by yourself. How do you do this? You have to gain experience working with a lot of problems. Okay, so here you go. You can go into the GitHub, and there is a very easy way in which you can create a linear regression function. Okay, and basically all the machine learning models behave something like this.